let's look at the solutions to the boundary problems. Once again, just because I post the solutions to YouTube, that does not mean I don't want you asking me. I'm here to help, but this gives you 24/7 access, and you're not competing for my time. So if this method works, you're good to go. But if you still don't understand it, by all means contact me. That's my job. Our first situation here is we have to make a decision. If I said to you, tell me how far this plane, a 200 meter a second object travels for 6 hours. How far have they traveled? You'd instantly know how to do it. But the minute I pose it as a problem, can they make their target? Instead of telling you how far have they flown, I can instantly cause confusion, because now you have a decision to make. What is it I need to know to decide this? So the question is not how long it takes them to fly 4,800 kilometers, but in 6 hours can they do it? Once you spot that, then you're literally grade 8 arithmetic. Step 1, the wind is slowing the plane down, and I gave you the speed of the plane and the speed of the wind in inconsistent units. Divide by 3.6. 200 meters a second west, 14 meters a second east. Let's west be positive and east be negative. So the speed of the plane has the speed of the wind removed. So the plane is really only traveling 186 meters a second, which is hella fast, actually. It's pretty dang fast. And the target is 4,800 kilometers away. There was a typo in the original lesson. I hope it's corrected here. What are our variables? Speed of the plane and the time of 6 hours, which is 21,600 seconds. What is the maximum distance? That's why I called it Dmax. This plane could achieve in that time. That should be pretty straightforward. The total distance you could travel is V times T, which winds up being around 4,000 kilometers. This bomber has no hope of reaching its target. We have to push the younger kids out of the plane and see if we can lighten the load enough to make it to the target. Now, what is the farthest target they could reach and still be able to get home? I'll do that later. Everyone has that running dream where you're running away from something. Well, the school board's going to try an attendance cheetah. And the attendance cheetah will be there to encourage students to get into school. So Ralph is approaching the school at a leisurely pace when he sees the attendance cheetah. So Ralph is 10 meters from the door when he sees the attendance cheetah break from the cover. 270 meters to the door is actually accurate for ODSS. There's a wood, like a little copse of trees at the back of the property, which is 270 meters from the door. And so the cheetah makes it out, and he's encouraging the boy to reach the classroom. The kid has 30 meters to go till he's at the door. He can run at 10 meters a second. The cheetah can run 120 kilometers an hour, but it's at 270 meters from the door. Bug. The animation came out backwards here. So little Ralphie boy, he can run at 30 meters. He has 10 meters a second. So the time of his run is 3 seconds. In 3 seconds, he's in the door. Oh, the cheetah goes hungry today. The cheetah has 270 meters to cover at 33 meters a second. So he makes it to the door in 8 seconds. So Ralphie makes his escape. His friends hanging around, texting and doing selfies, unfortunately, give the cheetah its breakfast. This is more like grade 10 math, and this gets more advanced. And I'm only teaching it to you to get you ready for grade 12, not to assess you on it now. If I say to you there are two cars, car B is just booking it at 50 meters a second. I'm coming along. And let's say this is a cop. And the cop is sitting here 100 meters ahead. And Ralph, this car B, goes by. That's significantly over the speed limit. So the cop, he saw the guy coming and knew he was speeding. So as the cop suddenly starts to speed up at the moment this guy shows up. So the guy's 100 meters behind the cop sees him coming, and he steps on the gas. So the cop, with a 100-meter head start, peels out onto the road at this acceleration. Will the cop catch up with B, or can you say, when will these two be at the same distance? So he can wave his fist at him. Pull over, sonny boy! This means these two should share at some point the exact same distance at the exact same moment in time. That will be the condition of an intersection. What I did here was use Google Sheets, and I plotted the two motions. This is the car doing 50 meters a second, and this is the cop that peels out, but he had a 100-meter head start. He was 100 meters ahead of the guy, and he's accelerating. And the two plots collide just over 2 seconds. Intersectional lines and curves, that's grade 10. You do more in grade 11. What does it look like in a pure mathematical solution? These two formulas, just like math class, distance B and distance A should overlap at the same time. So if I put them together like this, they're equal to each other. And I start collecting terms. At this point, I drop all my units, which is actually accepted practice in physics. Nobody wants you to track units through the quadratic. That's just getting psychotically cruel to do that. We begin to collect terms, and before you know it, you can follow the steps here. We wind up reducing it right down to a pretty straightforward quadratic in grade 10. I don't know why I did that. What's the quadratic formula? Minus b plus or minus b squared over minus 4ac over 2a. So if you plug in these two numbers here, get my trusty calculator out. 400 minus 160 is 240 square root a and plus 20 divided by 2. There's an intersection at 17.7 seconds, and on this one we get 160 square root, wait, no, sorry, not 160, 4, my internal math is shutting down. 400 minus 160 is 240. Square root of that. And so 20 minus 15.5. 20 minus 15.5 equals, divide by 2. The first intersection is 2.25 seconds. Why did we get two intersections? It's pretty easy to see. If I go to a drawing and we draw, the one car was doing this. That was its speed time graph. But the police officer was doing this. He was accelerating. Oops. Police officer was accelerating in his car. This means the red car passed him briefly at the 2.2 second mark, but then as the cop's acceleration started building up, he eventually would catch up again. So the two solutions to the quadratic actually have a meaning in the real world if we plotted it further than what you see. So if I back up here, you can see on this graph, this blue curve, if we kept following it, it's going to come back up and re-intersect. So that's what the two solutions to the quadratic mean.
Oh, shit.
Galileo supposedly dropped objects from the Leaning Tower of Pisa. The tower is 56 meters tall. How long would it take an object to fall? We itemize everything we've been given. then the easiest formula to use in this case, there's no VIT, and we get this rearrangement. Doing it as pure algebra works out better because I can see your logic and you get formulas for different things, and then you substitute your numbers in at the end. And we get 3.3 seconds. Now, the Leaning Tower of Pisa is about as tall as the Bromount Towers in Orangeville, something like that. And that seems a reasonable number. 3 seconds for a ball to fall from the top of a tower. You could close your eyes, picture the Leaning Tower of Pisa and someone throwing off the ball off the top. And your brain has so structured itself around this universe, you can picture that rate of fall. You can imagine it. You can imagine yourself having that falling dream, and you can get an idea that that is that's reasonable. If you got 33 seconds on a test, stop and go, wait a minute, 56 meters? 30 seconds? I've made a mistake. Here's a Perry's Victory monument, and the poor woman that was hammered by the stone from the upper deck. So we have a 107 high meter tower. Gravity is G, the initial speed is 0, and we want to know the final speed, and we don't have time. There you go. No time in the problem. This is the only equation that will do it one pass. If you decide to hammer around, you can get to the answer using 2 or 3 of the other equations. But to do it in one pass, this is the formula. We've got no initial speed. I'm just going to round. It's going to be 2 times 10 times 100. So it's 2,000. The square root of 2,000, it comes out to 46 meters a second unless I make a mistake. So it's booking. That's well past highway speed. Now, Canada's evil genius had a Harp Gun that fired at 2,200 meters a second upwards. How high would that shell actually go? What defines the boundary condition here? First of all, the curve on the left is showing a parabolic trajectory, but I said the gun was firing straight up. Many textbooks to show it went up and down will plot it on an angle, and then it might lead you to believe, oh, they fired it on an angle. No, when the question said straight up, it's straight up. Well, what determines, what characteristic exists at peak altitude? By the time you've climbed to maximum height, what parameter has dropped to 0? Well, clearly it's not going to go any higher than the moment of 0 speed, that exact moment that the tennis player is supposed to swat the ball. You toss it up and you wait for that, just that moment it halts. That's your boundary condition. When is speed 0? That will be at peak altitude. And that's the only hard part about this. Here's the information we have. Initial speed and a peak speed of 0, and the acceleration due to gravity, no time, and we don't have distance. We want to solve for it. And then we have these equations. We got to go, which one can we pick? If you don't spot that it's this one down here, then use process of elimination. This is not a constant speed problem. It's acceleration. That equation doesn't fit here. And all the others involve time, and I don't want to calculate time when I want distance. Can I calculate it without knowing time? Yeah, it's this one. Let's put our numbers in. Hear my little dramatic pause when I'm trying not to say so? A lot of you would do this. You'd put a number in here, 0 for initial speed, then you'd multiply, and now you'll try to isolate D. So you'll get this, and then you'll rearrange and dutifully write out everything your calculator spat out. This is tolerable, but it means that if you have, this is a 3-mark problem, and you put in the wrong number here, let's say you wrote 220, you now get no marks for the rest of the problem because you're wrong every step of the way now. If you learn to rearrange, instead. And remember, there's no VI. So I just simply take the 2A and move it down. You've rearranged the formula correctly. I would give you the second mark out of 3 right then and there, because you've shown me the correct rearrangement of the formula. And now if you're numerically wrong, you don't keep losing mark after mark. You just lose 1 or 2. I put in 2200 over that. I get 4840000 over 20. I get 242 kilometers. That cannon could shoot 240 kilometers up. Orbit is about 500 kilometers. So in the year I was born, this guy was shooting shells halfway to outer space. The question is, do you think the gun could ever actually reach this theoretical 242 kilometers? Contact me if you need any